Table 2, 1, V, I are symbols, units. Definition. Direct current, DC, states that electrical current flows through a resistor without changes in amplitudes or frequencies. A waveform can be used to make clear such phenomenon. A waveform is a time, transient, domain graph that shows quantities such as voltage, current, or power on the vertical, y-axis, time on the horizontal, x-axis, see Figure 1.2. In this waveform, the DC voltage level stays the same over time while the frequency of DC is 0. We will further define amplitude and frequency in Chapter 3, AC. Figure 1.2, Voltage versus time in DC. Ohm's law. Ohm's law states that when there is a voltage developed, drop, across a resistor, i.e., voltage difference between two resistor ends, nodes, electrical current is bound to flow. The mathematical relationship between voltage, V, current, A or amp, and resistance, omega. Voltage equals current x resistance. For a given resistor size, increasing voltage causes current to increase linearly. Thereby, Ohm's law is simply a linear function, see Figure 1.3. We can apply the above linear relationship among voltage, current, resistor, and slope concept to calculate resistance. A VI graph is shown in Figure 1.4. Any 2 points can be used to calculate slope, resistance. Because this is a linear function, straight line, slope, resistance is fixed. Resistors are usually in large sizes, thousands of S, sometimes even more. This is because, for a given voltage, large resistance results in lower current, linear relationship. This is essential due to safety and power-saving reasons. Using Ohm's law, 1V divided by 1A equals 1 omega resistance, 1V/1A equals 1 ohm. 1 ampere is a lot of current, in fact, current above 100 milliamperes, milliamp, going through the human body is deemed lethal. To lower the current for a given voltage at A. Figure 1.3, Ohm's law, a linear graph. Figure 1.4, slope equals resistance safe level, resistance needs to increase. For example, to lower the current to 1 milliampere, 1V source yields are equals 1V/1 milliampere equals 1000 omega or 1K. Note, K is equal to 1 times 10^3 is equal to 1000. Many portable electronic designs draw less than 1 milliampere of current to conserve battery life, resulting in large values of R. This explains why thousands or even hundreds of thousands of omega are frequently seen. Power. Power, P, definition. P equals I2x R or V2/R. The unit of power is watts, W, and its symbol is P. A modern smartphone power amplifier consumes about 300 milliwatt, in idle mode. With 4V lithium-ion battery, a popular cell phone battery type, antenna load resistance can be calculated. 300 milliwatts equals 42/R equals 53.33 ohms. Voltage source and schematic. A voltage source is an electronic device that supplies voltage to an electronic load. The electronic load acts as an output that delivers or receives electrical energy to and from an input. Load examples are motors, electric fans, lights, etc. An ideal DC voltage source has zero internal resistance, capable of sourcing, sending, and sinking, receiving, infinite current amount to and from the load. A non-ideal voltage source contains finite, non-zero, internal resistance and cannot supply or receive infinite current amount. The most common DC. Figure 1.5, alkaline battery types. Voltage source is alkaline household battery commonly used in portable electronics. Figure 1.5 shows several popular alkaline battery types, Energizer brand. Most alkaline batteries are cylindrically shaped except the 9V type, which is rectangular. They differ in sizes, voltage ratings, and mAh. mAh stands for milliamp hour, which is equivalent to electron charge. It describes the electrical current capacity of a battery. both AA, AAA, and D batteries and are rated at 1.5 V with different mA ratings. A 9V battery is rated at 9V DC, 1800, 2600 mAh. If, for example, a portable device draws 100 mA discharge current to operate, the battery will last a minimum of 18 hours. 1800 mAh/100 mA equals 18 hours. Other popular batteries are button-sized batteries, button cells, suitable for lightweight applications. They come in a wide range of types, sizes, and voltage ranges. Button cells typically are rated at 1.5 V with less mA, 150 to 200 mAh. Current source and schematics. A current source is an electronic device that supplies electrical current to a load. An ideal current source has infinite output resistance capable of supplying an infinite amount of current. Most electronic designs can be graphically expressed in the form of schematics, electronic circuits. Schematics include graphical V, I, and R symbols, plus various electronic components and wires. Figure 1.5a shows schematic symbols of voltage and current sources with ground connected at the other end. Ground is an electrical connection that is referenced to zero voltage potential, 0V. Schematics can be hand-drawn on paper, although the majority of schematics are entered into computer software. This makes it very easy to design and modify electrical schematics. Popular electronic schematic software tools will be discussed in Chapter 4, Analog Electronics. Ideally, ground is at absolute 0V with zero resistance. Keep in mind real-world ground has non-zero resistance. The ground signal amplitude depends on multiple factors, mostly from electrical noise, which will be discussed later on. The current source symbol in Figure 1.5a contains an arrow signifying the current flow direction. Both triangular and horizontal line ground symbols are interchangeable, although some use the triangular symbol strictly for power ground, the horizontal symbol for signal ground. Triangular ground symbols are used throughout this book. Figure 1.5a, voltage, current, and resistor schematic symbols. Electrons. An atom is made up of tiny particles, protons, positive charge, neutrons, neutral, and electrons, negative charge. Protons and neutrons are in the center of an atom while electrons surround the nucleus. Electrons are ions, particles, containing negative charges. Difference in electron and proton numbers gives rise to various atom structures, chemical elements. In this book, we mainly microelectronics, such as silicon, and attracted to positive charges, terminals, and polarities. The symbol Q quantifies electron charges. The unit of Q is coulomb, c. 1 electron charge holds. Focus on chemical elements that are used in germanium. The negatively charged electrons are 1 electron charge is equal to 1.6 times 10⁻19 C current versus electrons. In Figure 1.6, a positive voltage source, positive signs, is connected to a resistor with a wire. The other end of resistor connects to ground, negative polarity, creating a loop. Due to a positive charge at the voltage source, according to Ohm's law, a current is bound to flow through the resistor in clockwise direction, inner arrow, while electrons, E, are flowing towards the positive charges arriving at the voltage source. Keep in mind the electron and current flow in reverse directions. Figure 1.6, Electron versus current flow. Kirchhoff's voltage law, KVL. KVL states that the sum of all voltages around a loop equals 0. A simple circuit in Figure 1.7 applies and explains this theory. There is only one theory to apply, Ohm's law, and we will use it twice. This circuit contains a 5V voltage source connects to a 10 ohms resistor. We use ground to close the loop. By using Ohm's law, current can be evaluated. V equals IXR, I equals V slash RI equals 5V / 10 ohms equals 0.5A. This circuit is a series circuit. There is only one branch the current could go. We will visit more series circuits in a moment. Figure 1.7. Series circuit. By using Ohm's law the second time, we could find out what the voltage drop is across the 10 ohms resistor, V_resistor. V_resistor equals Ix, or V_resistor equals 0.5 A x 10 ohms equals 5V. Now, we could use all voltages in this circuit to see if KVL holds up. Sum of all voltages around a loop equals voltage source plus voltage drop across the resistor. 5V plus 5V equals 0V. It checks out. Notice that the voltage drop across the resistor contains a negative sign, polarity. The reason is that the voltage on the left-hand side of the resistor was higher, plus, than the voltage on the right-hand side of the resistor. The positive resistor sign opposes the positive polarity of voltage source, hence the negative sign in the KVL calculations, see Figure 1.7. The importance of this circuit is twofold. First, it demonstrates how simple it is to apply and explain the circuit using Ohm's law and KVL. Secondly, despite the circuit's simplicity, any electronic circuit, regardless of its complexity, can always be explained by Ohm's law and KVL. Sometimes, you will hear statements such as, there is a short in an electronic circuit that caused damages. Applying Ohm's law easily explains it. In Figure 1.7, if the 10 ohms resistor were shorted, zero resistance, and we applied Ohm's law, I equals V/R, where V equals 5V, R equals 0. I equals 5V/0. Omega equals infinite. Current becomes infinitely large, causing damage to the system. Realistically, any electronic system, no matter how shorted it becomes, possesses a finite amount of resistance. Kirchhoff's current law, KCL. KCL states that current going into, passing through, a point, node, is equal to current coming out of the same node. We could use the same circuit in Figure 1.7 to examine this theory. This is a series circuit. The current goes into left-hand side, node, of the resistor, and thus is equal to the right side of the resistor. We will use a parallel circuit in the next segment to further explain KCL. Parallel circuit. Series circuit states that current only flows in one direction. In parallel circuits, however, current flows in more than one direction, see Figure 1.8. Figure 1.8, KCL current IA, goes into node Z and is equal to sum of both currents IB and IC, coming out of the same node, node Z. Mathematically, it's simply IA equals IB plus IC. Parallel resistor rule. Equivalent resistance, R_equivalent, of two resistors, see Figure 1.9. Figure 1.9, parallel resistor rule. If the parallel resistor's number is 2 or more, the equivalent resistance is equal to the reciprocal of the sum of individual reciprocal resistances, see Figure 1.10. Figure 1.10, multiple parallel resistors. If A equals 1 ohm, B equals 2 ohms, C equals 5 ohms. You may notice that the equivalent resistance of multiple resistors is always slightly less than the smallest resistor among the resistor groups. From the above example, the equivalent resistance of 1 ohm, 2 ohms, and 5 ohms is 0.58 ohms. It's less than the smallest resistor value, 1 ohm. This gives you a quick way of knowing if the equivalent resistance you come up with makes sense or not. Note that if the resistor numbers in parallel are exactly the same sizes, the equivalence resistance is calculated as resistance of one resistor divided by the total resistor number. Example, 10, 10, 10 is equal to 3.33 omega. 10 divided by 3 is equal to 3.33 omega. This rule, however, doesn't apply to parallel resistors that have different sizes. Series resistor rule. Equivalent resistance equals sum of all resistances, see Figure 1.11. Figure 1.11. Series resistor rule lets use a simple parallel circuit to explain series and parallel resistor configurations. See Figure 1.12. Figure 1.12, simple parallel circuit. In this illustration, resistor A, B forms a parallel circuit. total current I underscore total, going towards node A, B is divided into two separate branches, according to KCL. To calculate I underscore A, I underscore B, we first calculate the total resistance of the entire circuit. I underscore total can then be found. The idea is to consolidate all three resistors T, 10 ohms, A, 10 ohms, and B, 10 ohms, into one resistor, equivalence, and one voltage source. We can then use Ohm's law to calculate I underscore total. According to figure 1.9, resistor A, B can be combined into one resistor, R underscore EQ.